In this video, we're going to look at the effect that variability has on the processing of the wafers. And in particular, if we look at this system as was set up in the problem, if we assume that there's no variability in the system, that is, the rate of arrival is going to be static and the rate of service is going to be static, and they're going to occur exactly on those intervals, then the rate of job arrivals is 3 wafers per hour, and of service time is 1/4 per hour, which gives us a service rate of 4. Right, so on average, we could put through 4 wafers per hour. In this case, where there is no variability, the waiting time in the queue is 0, because the service time, or the service rate, is greater than the arrival rate, or the time that it takes to service the wafers is less than the inter-arrival time of those wafers. Now, if we assume that there is variability in the system, and in particular if we assume that we have Poisson arrivals with exponential services, we know that the expected waiting time in the queue is going to be given by this expression, where rho is going to be the utilization of the machine, or lambda over mu, as shown here, and LQ is the number of jobs, or the average number of jobs waiting in the queue. So the waiting time in the queue then is LQ divided by lambda, which is this expression. Plugging in our lambdas and mu's, we get 45 minutes. So this shows the effect of variability. If we assume there's no variability, the waiting time in the queue is 0. But if we assume that there is variability, then the expected, or the average waiting time in the queue, is 45 minutes.